Good afternoon, everyone. Thanks for coming to my lecture. My name is Giray Ökten from Florida State University. And my first two lectures will be on this topic, number sequences for simulation. And what exactly do I mean when I say number sequences? Mostly I'm talking about pseudorandom numbers that we use in Monte Carlo simulation and low discrepancy sequences that we use in quasi-Monte Carlo simulation. The low discrepancy sequences have other names. Sometimes we use the term uniformly distributed modulo 1 sequences, or QMT sequences, or quasi-random sequences. And before I talk about pseudo-random and low discrepancy, I want to say a few things about random numbers, or random sequences of random numbers, which is like an abstraction for pseudo-random numbers. And that's going to give us a nice perspective before we talk about pseudo and low discrepancy sequences. Now, this is a typical example people would use when discussing randomness. If you look at these three finite sequences, these three strings, binary strings, zeros and ones, and then if we ask the question, which one of these binary strings look random, then, well, definitely one would say the first one does not look random at all. It's just all zeros. And when you look at the second and the third one, you may think they look random. Maybe there's no pattern that you can find. And in fact, the last one is obtained from actual coin tossing, where one is tails and zero is heads. And the second binary string was obtained from the first 20 digits of this number, square root of 2 minus 1. And of course, the first one is the constant string. If you think 0 or 1 equal probabilities, 1/2, realize that the probability of every string that we have listed in these bullets are actually the same.
Excuse me, Mr. Ökten?
Yes.
Is it possible, I think there is some lag, to put your camera in medium definition, maybe? Are you on Wi-Fi or?
I'm on Wi-Fi, yes.
Yeah. Do you think it's possible to put you on, or to change the quality of your webcam and use medium quality, maybe?
Let me try that. Okay, so medium quality is what I'm trying right now.
Yeah.
Is it good?
Yeah, we are going to try like this. If you can start just a few seconds.
Okay. Maybe from the beginning of this page.
Okay. Okay. Thank you.
So here's a simple example that we can plus to understand some important issues for the concept of randomness. At these three binary strings and pose the question, which one of these binary strings? Oh, I'm sorry, I have to go back. Can I start from this page?
Yes. Okay.
Okay, thank you. I'm starting again. To understand more about the concept of randomness, people in the literature typically use an example like this. So here in this example, you see three finite sequences These are 20 binary strings in each case. In the first one, you have all zeros, and in the second one and the third one, you have a bunch of zeros and ones. And the question is, which one of these binary strings look random? Now, you would, of course, certainly, say the first one does not look random at all because it's all zeros. And looking at the second and the third one, you might say, well, they both, probably look random enough. And in fact, only the third one is obtained from an actual coin tossing. The second outcome was simply the first 20 binary digits of this number, square root of 2 minus 1. And the first one is, of course, the constant string. And what's interesting in this example is that if 0 and 1 occur with equal probabilities, with 1/2, then all of these binary strings have actually the same chance of happening. In each case, the probability of occurrence is going to be 1/2 raised to the power 20. So that tells us that whatever we understand what randomness is, it has nothing to do with probability of occurrence. So then, what is it? What is it? What do we mean when we talk about randomness? There have been several approaches to define randomness, and in this talk, I will try to summarize two approaches. And here's the first one. This is called randomness as incompressibility. Now, what we want to do is look at the example that we talked about a minute ago, and then think about perhaps how to find a pattern, if we can, and then write a computer program that would output these outcomes. So for example, here in the first one, these are all zeros. The pattern is obvious. So you would say to the computer, print 0 20 times. That would be the algorithm. That would be the computer program that's going to relay this information to the computer. All you need really to do is represent 20 in the hard disk. So that's why I say this string can be coded using a little more than log base 2 of 20 bits. In the last string of actual coin tossing, if we cannot find a pattern, then we will have to write each digit one by one in the computer hard disk, and that would require 20 bits. So then the intuition is the second bit looks more random, more difficult to generate it in terms of a computer program. So this intuition is used to define the algorithmic complexity of a string. So the algorithmic complexity K, string x1 through xn, is defined as the size of the smallest input program that outputs the string when fed to a Turing machine. If you don't know what a Turing machine is, just think of it as a computer or as a mathematical model for a computer. So we are trying to find the smallest input program for our computer that will output this string. And then a sequence is random or incompressible. This is the definition in this approach, if it has initial segments of high algorithmic complexity. Okay, so it's not a very formal definition, but what we are trying to say in this definition is that we define randomness as having high algorithmic complexity. And here's another approach to randomness. This is referred to as randomness as typicality. And now instead of finitely many digits, let's think about infinite sequences of binary digits. Here's an infinite sequence of zeros and ones. Now, if you have an IID, a sequence of Bernoulli random variable, and then you would want this sequence, infinite sequence, to satisfy all properties of an IID sequence random variables that are satisfied with probability bar. For example, you would expect the relative frequencies of 0 and 1 to converge to 1/2. Okay, and then you can also think about relative frequencies of 0, 0, 0, 1 and other pairs, find the correct probabilities, and then you require the relative frequencies to converge to those correct probabilities. You know, intuitively, any theorem that you can write about the behavior, any property you can mention about the behavior of 0, 1 ID random variables require this sequence to satisfy that. And as this infinite sequence satisfies more and more of these properties, it will become more typical in a sense. And in this approach, this definition by Will, you define a typical sequence, hence a random sequence, to be a sequence that satisfies all properties that occur with probability 1. It turns out that this is too restrictive. You know, you cannot really find a random sequence that satisfies all these properties. And Martin Löf restricted this definition a little bit, and he defined a Martin Löf random sequence to be a sequence that satisfies all Turing computable properties that occur with probability 1, as opposed to all properties. What is a Turing computable property? Well, just think of it as a property that can be easily checked using a computer program. And it turns out that these two notions of randomness that we talked about are equivalent. And so once again, Löf random sequence is a sequence that satisfies all Turing computable properties that occur with probability 1. I'm going to use this as a definition of a random sequence, and then think about this a little bit. And then I'm going to ask the question, so can we see an example of a Martin Löf random sequence? Because we need these random sequences, we need them in applications. And the answer is no, it's a disappointing no, because an element of a Martin Löf sequence is actually non-computable. There's no algorithm that generates its digits. So we almost have a paradoxical situation. We have a nice definition of a random sequence, but we cannot compute it easily, or we cannot compute it at all. If we could actually compute it easily, there would be a pattern to it, and maybe it's not going to be random. So we have to strike a balance somewhere. So that takes us to pseudo-random numbers. So what is this? What are pseudo-random numbers? If a Martin Löf random sequence is a sequence that passes infinitely many, well, before on the previous page, the definition was it satisfies infinitely many properties. I'm going to rephrase that. I'm going to say it passes infinitely many tests. So a test is like checking if the sequence satisfies a property or not. And if it satisfies, you say, it passes the test. Okay, and here comes the definition of a pseudo-random sequence. It is a sequence that passes only finitely. In the literature, we actually call these statistical tests. So that's the compromise we are doing. We cannot generate Martin Löf random sequences easily, or not at all, because of this restriction pretty high. So from infinitely many, if you go down to finitely many, that takes us to the definition of pseudo-random sequences, which are going to be much easier to generate. You might say, what does finite mean? And here's a quote from Knuth. He wrote, in practice, we apply about half a dozen different kinds of statistical tests to a sequence. Passes them satisfactorily, we consider it to be random. It is then presumed innocent, proven guilty. Very well-known example of a pseudo-random number generator or a sequence is linear congruential generators. These were introduced by Lamer in 1949, and this is a simple, congruence relation. Xn is congruent to a number A. It's called multiplier, multiplied by the previous element of the sequence, plus some number called the shift. And this arithmetic is done mod m. And the outputs of this recurrence, x1, x2, x3, so forth, are then divided by the modulus itself, by m, and that produces numbers between 0 and 1. We will see more examples of pseudorandom number generators in a little bit. Now, what about low discrepancy sequences? There's the second type of sequences that we talked about that we use in simulation. So let's do a quick reminder. Martin-Lev was a sequence that passes infinite limited tests. Pseudorandom was a sequence that passes finite limits. Low discrepancy sequence is a sequence that satisfies really just one property. Its definition, one defining property, and that's what matters. And in this lecture, we will talk about some pseudo-random number generators, and this will be a quick, brief summary of different types of generators that we have. And then we'll talk about low discrepancy sequences, and we will compare them. One point is that when we talk about a pseudo-random sequence, we typically talk about numbers coming from the uniform distribution on 0, 1. And if we need pseudo-random numbers from another distribution, then we apply an appropriate transformation method. That's something we're going to talk about in the third lecture. Also, I want to point out that we try to keep the interval open. You don't want to have a 0 or 1, which can cause problems in your computer code. If you're dividing by a random number, you don't want that number to be equal to 0. This is not a theoretical issue. It's just a practical consideration. So in practice, a pseudo-random sequence should not output 0 or 1. We already briefly talked about linear congruential generators, and here is it again. And if this shift C is taken to be 0, which was actually the original LCGs Lehmer considered, we use the term multiplicative congruential generators for them, MCGs. Now, since a linear congruential generator is coming from a recurrence mod m, it can only produce at most m distinct integers, 0 through m-1 in some order. If you have a multiplicative congruential generator, you cannot possibly have a 0, because if you ever 0, the generator outputs 0 all the time. So that's why you want to exclude 0. We can have at most m-1 distinct non-zero integers. Now, this number of distinct numbers the generator can produce is an important concept. It's called the bit of a generator. And in practice, of course, we want that period as large as possible. Now, here's a little, a silly example. I say it's a silly example because it's a very small modulus. It's an LCG with multiplier 5 additive constant 4. And I take different seeds, x0 to be 0, 1, 3. And if you take x0 to be 0, the different outputs that this generator gives are 0, 4, 8, 12, and then it's going to start repeating itself. If the seed is 1, if x0 is 1, then you just get 1 and 9, and then it's going to start repeating itself. If x1 equals 3, actually, you don't get any other number. So this silly example tells us that we need to be careful when we are choosing our linear congruential generator. And the period may depend on the seed x0, which is not a good thing. Okay, we want to avoid that, so that if we pick an unlucky seed, we don't end up having a very poor quality, a random number generator with a short period. And also it tells you that if you're not careful, you can have period much shorter than the maximum period possible, m. Now, if all you care about is to obtain the largest possible period, you can think about a generator like this. Xn is congruent to xn minus 1 plus 1. Then you can start your seed at 1. clearly, what this sequence generates is going to be far from looking random. Yeah, so those are two things that we want to obtain. We want to obtain a large period, but at the same time, we want our numbers to look random. And here is a classical result that tells us the conditions, and this is a full characterization, it's an if and only if statement. It tells us the conditions for an LCG to have a full period. The period of this LCG is M, the modulus is M, and the period is M if and only if three conditions are satisfied. And as you look at these conditions, the first one, greatest common divisor of C and M equals 1, and then you have these restrictions on the modulus. Not modulus, it's the multiplier A. So this theorem gives us an easy tool, or a tool to design LCGs with full periods. At some point many years ago, when I was first preparing these lecture notes, the rand function for Unix BSD version was using an LCG of this sort with modulus 2 to the power 31. And there are other LCGs that do not have full period that are used in practice. I don't want to go into too many details, but in this case, this type of an LCG was at one point used by Maple. And then this type of LCG with these specifications at one time was used in Cray supercomputers. Now there's an interesting result, a theorem proved by Marsaglia in 1968, which tells us that all LCGs have a similar property. The property is that, well, let's just read this, the output of any LCG lies on a simple lattice in a K-space with axes representing successive numbers in the out. But I don't think this is a very easy statement to understand, but it's going to be much easier if we look at an example. So here's an example. I'm looking at an MCG. MCG is just a special LCG with modulus 31 and multiplier 3, and I'm starting at 9. I see it. And there you go. Here are the numbers. Well, I said I'm starting at 9, but I'm really starting at 27 here. And then here I come back to 27, and that's the end. Now, when you look at these numbers one by one, you may think it looks like a random sample from the uniform distribution, over the integers 1 to 3. Then if you partition this list in an overlapping way, so 27, 19, 19, 26, 26, 16, that's what I mean by overlapping. And I also partition it in a non-overlapping, so non-overlapping, the first two, the second two, the third two, etc., and you obtain the following figure. If you look at this now, what you see is that the output of the LCG lies on just 3 lines in the unit square. Now, this is not a very encouraging result. It tells you that your random number generator, pseudorandom number generator, is missing to represent all the spaces between the 3 lines, and that's huge. So Marsaglia's theorem tells us that all LCGs have this structure. So what you try to do is you try to find better ones where there are like more lines, or in general more hyperplanes. And one to measure the quality of a pseudorandom number generator is by looking at the distance between these 2 lines, or in general the distance with hyperplanes, and then you want to make sure that distance is as small as possible. and you use that distance as a quality of the generator. Now, Randu is a famous example of a faulty MCG, which was widely used in the 1960s. And it was first found to be faulty when some people applied it to problems, to some simulation problems, and they knew what the answer to the problem was. They were testing the MCG, and then it gave incorrect results. I'm not going to go through these derivations, but here's the generator. Xn is congruent to this multiplier times xn minus 1 to the power 31. Below the derivations, you end up with this equation. This tells us that this is the equation of a plane in the three-dimensional space. And this tells us that the triplets obtained from Randu must lie on no more than 15 planes in R-cube. And that is a small number. That's an insufficient of insufficient quality. I want to briefly and quickly talk about some different types of pseudorandom number generators. Quadratic generators. These type of generators, Xn is not just, it doesn't just depend on a constant times Xn minus 1 like in LCG, but we also see another term square of Xn minus 1, right? Making recurrence more complex. Now, like Fibonacci generators are coming from the classical Fibonacci sequence or Fibonacci generator. This one as a random number generator is pretty bad. But then if you generalize this so that instead of n minus 1 and n minus 2, you look at some general lags, differences like n minus r and n minus s, then you can get some, good quality pseudorandom number generators. And there are more generalizations of these type of generators. This operation plus could be replaced by some other operations. This is an example of a lag Fibonacci generator taken from Knut's book, Computer Programming. When I point out to the huge period the generator achieves. Then there is the multiple recursive generators where the nth term of your sequence depends on the first k, the terms, and not p prime. It's possible to find the coefficients a1 through ak such that the sequence, the xn's, has period of length e to the power k minus 1. In a special case when p equals 2 is commonly used today, and here's that special case when p equals 2, and here's my recursion, and it turns out that the period of this generator is 2 to the power k minus 1 if and only if the polynomial at the top, which is obtained from constructed using the coefficients that you see here, is irreducible. These generators were introduced in 1965. Now, feedback shift register generator. Take those zeros and ones that we talked about in the page, and then it blocks them. So for example, I'm taking the first 4 digits and the second 4 digits, and then I'm going to turn each block of digits into an integer. And for example, in this way, 0 would be the coefficient of 2 to the power 3, and 1 times 2 to the power 2, etc. So these blocks will give me integers, and then I can divide those integers by the largest number you can get from the block that will give you numbers between 0 and 1. If you partition the blocks in such a way that there is a delay between blocks, then the so-called sequences are named as generalized feedback shift register generators. An example of which is the Mersenne twister. Twister is a better version of TT-800, and Mersenne twister is now common in statistical and mathematical software, programming languages like Python, excuse me, Julia, Mersenne twister as their random number generator. There are some other congruential generators. Here's an inversive congruential generator, where now we see the inverse of xn. And in general, you can think about examples where xn plus 1 depends on function of xn. And here you see some examples of more complicated nonlinear congruential generators. And finally, a method is to combine simpler generators to obtain a better quality generator. So if you look at this one, you see 3 CGs, 3 multiplicative random number generators, a pretty small modulus. But then if you combine the outcomes that you get from these sequences in this way, where you add them up and take the fractional part, the numbers UN, excuse me, give you a sequence with a period that is huge. It's 10 to the power 12. Another such generator was introduced by Lequier. Here I'm referring to a book by Paul Glasserman on Monte Carlo methods in financial mathematics. And I usually tell my students to take the algorithms from the book and write a code for some of these sequences. Now, faulty generators, faulty pseudorandom number generators is not something that only happened in the past. There is a fairly recent incident when a faulty random number generator appeared. This generator was mentioned in the first edition of a popular book back then, Numerical Recipes in C, and the name of the generator was RAN1. And a student, a master's student at Columbia University, was using this generator as financial math, an option from financial mathematics. In particular, this is a collateralized mortgage obligation problem. And it turns out that this problem really reacted in a bad way with the random number generator. Because the cycle, the pricing of the problem amounts to a high dimensional integral, a 360 dimensional integral. And that 360 was the key number that exposed the problem with the generator. And here I wanna show you, this is a plot actually that is similar to the plot from the master's student of the student. Student's name is Pascal, and Joe Traub was his master's advisor. And these different plots, except for the solid one, correspond to a simulation using the random number generator using a different seed. Every time the seed changes, and we are plotting price of the option, the Monte Carlo estimate for the price of the function as a function of the sample size. So this plot tells you that as the sample size gets larger and larger and larger, the option price seems to be converging to some value around here. But then you change the seed and you get different different values. So that's how people realized that this generator was not good. And it's a typical suggestion to ask users in simulation to have multiple random number generators, pseudo-random number generators in their arsenal. And certain Mercent twister is one of the best random number generators used today. And having more than one different kind of random number generator, good idea. Okay, now let's talk about low discrepancy sequences. Here's the definition of a UD mod 1 sequence. So we have numbers, a sequence of numbers in 0, 1. Now let's look at that summation. This 1ab, this is the indicator function. So this function gives 1 if xn is between a and b and 0 otherwise. So then what I do is I look at the first capital N terms of the sequence, x1 through x capital N, and I add these indicator functions when they're applied to the xn's. And that number is simply the number of xn's that lie between a and b. And I divide that number by n. That gives me the fraction of numbers, or fraction of the number of elements of the sequence that are between a and b within the first capital N. And then I take the limit of that fraction, or we can also call that the relative frequency, and I want that limit as n goes to infinity to be equal to the length of the interval. This is in dimension 1. Easily generalize this to a higher dimension. Case 0, 1 will be replaced by the s-dimensional unit cube, and the interval AB placed by this hyperrectangle. And then B minus A is going to be simply the measure, the Lebesgue measure, the volume of the hyperrectangle. Now, why are these sequences important? These sequences are important applications for the following result. If I have a function f, and this function f has an interval, and if I then the limit of the average of function values will be equal to the interval of the function as n goes to infinity. If the xn's are coming from a UD mod 1 sequence, tells us that we could estimate integrals by taking large values for capital N and computing these averages. And then we can measure the quality of a sequence by the relative frequencies differ from the actual volume of the interval. So let me just go over this definition carefully. So let's take an interval AB. This is a hyperrectangle, a subset of 0, 1s. And then I'm going to count the number of my the elements of my sequence xn that fall in this interval from A to B. And then I'm going to divide that number by capital N. So that's going to tell me the ratio or the relative frequency of the elements x1 through x capital N that fall in that subinterval, that hyperrectangle. And I know that in the limit, if xn was a UD mod 1 sequence, in the limit, this average is supposed to converge to the measure, the Lebesgue measure of this hyperrectangle. So I'm going to subtract that value, that limiting value, my summation, and I'm going to look at that difference. I will look at the supremum of that difference for all possible intervals AB. worst case analysis that tells you the worst deviation of the averages from their limit. If you change these intervals so that the left endpoint is always the origin, and then take a supremum over this family of intervals, then you obtain the so-called star discrepancy. And theorem from the theory of uniform distribution that the discrepancy goes to 0 if and only if xn is a UD mod 1 sequence. Sequences with the best known bounds for star discrepancy satisfy big O log n to the power s divided by n. And really technically the term low discrepancies are used for sequences that have this bound for the star discrepancy. And here I'm going to give some examples of sequences. This is the classical van der Corput sequence in base 2. And so how do we construct this sequence? Well, if I want to find the second term of the sequence, I take number 2 and I write number 2 in its base 2 expansion. So this is 1, 0, that's number 2 in base 2. And I will do this inversion operation. It's like taking the mirror image of this number. You flip this number 1, 0 over a decimal point. You put a decimal point and then you like take the mirror image, you flip it, that becomes 0.01. And this decimal in base 2 is equal to 0 times 1/2 plus 1 times 1/4. So that's your van der Corput, the second van der Corput element. And well, let's give a more mathematical definition. And by the way, anything that we did here, this is base 2. Everything that we did here in this table can be generalized. You can take any number. Instead of 2, you can take any number b. So here's the formal definition for any base b. If I want to know the nth term of my van der Corput sequence in base b, what I need to do is write n in its base b expansion, which is this, and then flip this and turn this into a decimal, okay? And that means that value. So that's the definition, the van der Corput sequence. The van der Corput sequence gives you a sequence in one dimension. If you take several van der Corput sequences and then couple them together to obtain a higher dimensional sequence, well, that's the Halton sequence. And if these different bases, B1 through Bs, if they are prime, then the Halton sequence is a UD mod 1 sequence.